Welcome, everyone. In this session, we have Apurvaa Subramaniam, data scientist at Amazon, presenting key takeaways and lessons learned from a newcomer to causal inference. Just a quick note that please post your questions to the Q&A box instead of the chat. Apurvaa, a reminder to start your timer. Off to you.
Thanks, Catherine. Hello, everyone, and thank you for attending my talk on causal inference. I want to start by briefly introducing myself. So I started my career as a software engineer in Singapore and then came to the US in 2015 to do a master's in analytics, after which I joined Amazon in a data science role. I worked on data science projects at companies from different industries, and that's one thing which I really like about data science is that it's relevant to pretty much every industry. So let's dive into the topic for today. What is causality? In simple terms, causality is about understanding cause and effect. It helps answer the question, why? Why did something happen? So why is this important? This chart shows the correlation between chocolate consumption per capita on the x-axis and Nobel laureates adjusted for population on the y-axis. So imagine if the government of a country looks at this chart and decides to introduce policies to encourage chocolate consumption, hoping that this would lead to more Nobel laureates. That obviously sounds ridiculous because this is clearly an example of correlation does not imply causation. Clearly, there are hidden or confounding factors because of which Switzerland has so many more Nobel laureates adjusted for population compared to other countries. But this is why it's important to infer causation correctly to ensure that the right decisions are being made. Most machine learning-based data science is in the association realm, which is at the bottom of the causal hierarchy. And that is why a lot of ML models tend to fail when they encounter data that's different from the data they were trained on, or when the underlying data changes. But when you go to the top of the causal hierarchy, that is counterfactuals and causal inference, the models become more robust and scalable, because once you understand the mechanism of why something works, it's easier to account for changes in data. So how do we infer causality? The gold standard is to run well-designed randomized experiments. However, this is not always possible or not ethical. So for example, if you want to study the effect of weather, say rainfall on coral growth patterns, it's not possible to run controlled experiments because we can't really control rainfall. Facebook a few years ago wanted to study how the sentiment of newsfeed content affects user behavior. So they ran experiments where some users saw mostly positive posts and others saw mostly negative posts on their newsfeed. And then they looked at the difference in behavior between these groups. However, when people found out about this, when media reported on this, there was an outcry because people felt that it wasn't ethical to manipulate user emotions in this manner. So when we can't run experiments, we have to rely on observational data to infer causality. There are two main frameworks which are widely used, structural causal model and potential outcomes framework. The end goal for both of these models is the same, or for both of these frameworks is the same, but the methodology and assumptions differ. So the techniques I will discuss in my talk today are from the potential outcomes framework, because in general, this is easier to understand. So why is causal inference difficult? One key issue is that there is no ground truth since the counterfactual cannot be observed. So an individual cannot be in control and treatment at the same time. And so no one really knows what the right answer is. And there's no validation or test set which you can evaluate your model performance against. And so assumptions and domain knowledge become very important. Problem specification is also crucial, which I'll talk about in more detail later. And a lot of causal inference techniques require high quality data, especially panel data, which is multidimensional data where you have observations for the same subjects over time. So the data requirements for causal inference are much stricter than for association-based models. Now let's talk about a real-world causal inference project I worked on at Amazon. So warehouse space is limited and it's very expensive. It costs millions of dollars to build new warehouses. So it's very important for us that we use warehouse space efficiently. So the goal of my team is to optimize inventory space for FBA sellers. FBA is a program called Fulfillment by Amazon, which basically lets third-party sellers send their inventory to Amazon warehouses, and then Amazon takes care of the rest of the supply chain. So Amazon makes the final deliveries to customers. What we found out was that several sellers were using Amazon warehouses as storage spaces for slow-moving inventory, which is bad for customers because this space could be better used for products that customers actually want to buy. So we came up with a number of capacity management solutions. One of these is called SMS, which stands for Storage Management System. And this system basically restricts the space for certain FBA sellers based on what we call the IPI score. So sellers below a certain IPI threshold are called low IPI sellers, and they're subject to these storage limit restrictions. And you can think of IPI score as a credit score for sellers, which basically measures the inventory performance. And this policy was introduced in Q3 of 2018. So the problem statement for this particular project that we started off with is, what is the impact of SMS on constrained sellers in Q4 2019? So Q4, which is the holiday season, is typically our busiest time, and space is usually most constrained at this time. And specifically, we want to look at two metrics: gross mean sales, which is the total dollar value of sales from that seller, and inventory volume, which is the total space occupied by the seller's inventory in Amazon warehouses measured in cubic feet. So we want to know, what would GMS and inventory volume have looked like for these sellers had we not subject them to SMS? And we can't run an experiment in this case because it would be unfair to randomly give unlimited storage to some low IPI sellers and not to others. And so we have to rely on observational data, which in our case is panel data at a weekly seller product level. So we tried 3 different methods. The first one, called difference in differences, or DID, is a method which basically tries to simulate an experiment. So this figure shows at a high level how this method works. On the x-axis is time, which is divided into 2 sections, pre-intervention and post-intervention. So this vertical line at the middle is the treatment or intervention. So in our case, the week or the time when the SMS policy was announced. The y-axis is the outcome of interest, which in our case is GMS or inventory cube. The red line shows the treatment group, which in our case is the constrained sellers, and the green line is an appropriate control group. So before the intervention period, there's a parallel trend between these 2 groups. But once the intervention takes place, there's a divergence in the parallel trend. And this divergence is what we call the intervention effect or the causal effect because of the treatment. So the reason we first tried this method was because this method was first used in Q3 2018 when the SMS policy was first introduced. And we had to extend this to a triple DID because instead of using just 1 control group, we had to use 3 control groups because we are accounting for 2 confounding factors. So we couldn't just use Q3 2018 high IPI sellers because we know that there are intrinsic differences between high IPI and low IPI sellers even without SMS. And we couldn't use Q3 2017 low IPI sellers because 2017 and 2018 are different years. And so there's different macroeconomic effects. So the idea was that we would just repeat this analysis, but using Q4 2019 data. However, when we tried to do this, we found that the key assumption for DID, which is the parallel trend in the pre-period, did not hold. And we also realized that the 2017 seller cohort was actually quite different from the 2019 cohort because in those 2 years, the seller composition had changed. So for example, there were a lot more China-based sellers whose inventory patterns are quite different. And so this was not a good control group. So the key takeaway from this was that assumptions which held previously may not hold any longer because of underlying data changes. The next method, called fixed effects regression, is basically a regression model which allows you to control for unobserved individual characteristics. So in our case, this would be seller characteristics such as seller business acumen or how much risk a seller is willing to take, which affect the outcome variables but are often impossible to derive from data. But they also act as confounding factors. This method is also more interpretable because it allows us to measure the effect of being constrained as well as the effect of level of constraint for sellers. And we also realized while running this model that we needed to refine the problem statement to account for the fact that some sellers in our cohort in Q4 2019 have already been subject to several quarters of SMS. So this is a different scenario from Q3 2018 when it was a new policy. And so for some sellers, the seller behavior has adapted to this policy. We also aggregated weekly data to quarterly for this model because the SMS policy is at a quarterly level and also for model simplicity. And finally, we decided on 2 validation checks to evaluate whether the model was behaving correctly. So the first is to run the model using the Q3 2018 cohort of sellers. The reasoning here is that the Q3 2018 effect from the fixed effects model should be similar to the triple DID, which was run previously. And we also wanted to run this for Q4 2017 cohort, which was before SMS was introduced. And the idea here was that there shouldn't be any significant effect because SMS wasn't introduced at that point. So I'll skip over this for now, but this basically shows the regression equation and the different components. So while running this model, we also realized that seller data is actually quite skewed. There are some very small sellers and some very large sellers. And so the treatment effects of SMS is different on these different types of sellers. So there's heterogeneity in treatment effects. So one way to account for this is to use log transformation. But when we tried running the model using level versus log data for the outcome variables, we realized that the results were very different, which meant the model was not robust to these transformations. And the validation checks, which I mentioned earlier, also failed for this particular model. And we realized that there was a loss of information because of aggregation to quarterly data. So the key takeaways from this method were that data decisions such as granularity transformations, etc., do matter. And more importantly, it's crucial to dive deep, understand, and refine the specification of problem statement. So the final method that we tried is called synthetic control. This is a more generalized version of DID. It basically allows you to create an artificial control using a weighted combination of groups instead of using a single existing control group. So this red line here is the treatment group, and the blue line is this artificially created control group, which perfectly matches the treatment up to the point of intervention. And then once the intervention happens, that is once the SMS policy has taken place, there's a divergence because the synthetic control group is not subject to the treatment. And so this is the counterfactual and this is the observed. So the difference between the counterfactual and the observed is the causal effect or the treatment effect due to SMS. So for this model, we used weekly data starting 2019. And we also used this at a seller level. That is, we created a synthetic twin for every seller. And this is basically to account for heterogeneity in treatment effects. Because once we have seller level effects, we can aggregate them in multiple ways, such as weighted average instead of using a simple average. Both the validation checks mentioned earlier passed for this method. And this method also uses fewer assumptions and is also easier to automate. So this is the method we finally decided to use. So here I've summarized my key takeaways and things to think about before you embark on a causal inference project. The first step, which is the most important and also probably the most difficult, is to understand the problem statement in depth, specify correctly, and with as much detail as possible. So for example, this was the problem statement we started off with, but several iterations later, this is the problem statement we ended up with. So this has a lot more detail and specificity. Also think about questions such as what decisions will be made based on this analysis? What are the different use cases? Do you want this analysis to be one-off or repeatable? Also think about how the data you're analyzing is generated, especially confounding factors such as previous policies or level shifts, trends, changes in seasonality, etc. And think about how you'll model these or control for these in your model. It's important to understand model assumptions clearly and think about whether they will continue to hold in the future. Design details such as data transformations and manipulations, what granularity of time you're using, as well as the treatment unit, whether you want to analyze at a seller level or a cohort level, are all very important decisions. Robustness and validation checks, you should decide on them before starting the modeling process. And you should take into account factors such as false positives and negatives. Another good way to do this is to run different models, and hopefully all of them will give similar results, which helps which is a good way to validate your model. So finally, I'd like to introduce a relatively recent topic called double machine learning, which brings together predictive power of ML techniques with causal effects from econometric causal inference techniques. So at a high level, the idea here is that given a set of control features X, we want to estimate the effect of treatment T on outcome Y. So we divide this causal inference problem into two prediction problems. The first is to predict outcome from control. Second is to predict the treatment from control. And basically you calculate the residuals in both these cases. And then once you have and for each of these prediction problems, you can use any of existing ML techniques such as neural networks, trees, etc. And once you have both of these residuals, then the final resulting coefficient gives you the causal effect of T on Y. And this method is something which a lot of teams at Amazon are now exploring. And finally, I've put together some references and resources to help, which you can refer to for further reading on the various topics that I mentioned. So that's all I have for now. And now I'll move on to answering any questions that you might have.
Great. Thanks for the talk, Apurvaa. Yeah, we'll now transition to Q&A, look at the Q&A tab for questions from attendees. We probably have time for maybe 2 or 3 questions.
Okay, so the first question is from Divya. How did you create the synthetic control group, and how did you assign the weights? Yeah, so this is a great question. So there are different ways to create the synthetic control group. What we used was matching on the outcome variables themselves. So in our case, the outcome variables were GMS and inventory cube. So basically, for the treated sellers, we looked at that data before the intervention period, so in the pre-period, and then we ran several synthetic control algorithms, which basically are optimization algorithms, which look at the control group of sellers. And for those two outcome variables, they create weights such that the synthetic control perfectly matches the treatment control in the pre-period before the intervention. Some other ways to do this are you can also introduce other attributes. So instead of just matching on the outcome variables, you could also introduce other attributes which, based on domain knowledge, which you think would affect the outcome. So for example, tenure of seller, or the type of products they sell, which country they're selling out of. Those are some attributes which you could also match on to create the synthetic control group. And that's something which we plan to do in the next iteration of our model. And so the weights are basically assigned by the algorithm itself. Okay, so then the second question is from Dita. What sort of tests do you use to determine if there's a significant effect between the treatment and control groups? So again, this depends on the type of experiment you're running, but common tests are t-tests, for example. That's a common test to determine if there's a statistically significant effect between treatment and control groups. But this, I would say, is an entire topic by itself, because depending on the type of metric you're measuring and the type of experiment you're doing, there's a whole set of tests that you can run.
Great. So I think that's time. Thank you for the great talk, Apurvaa. This concludes our session. If you have additional questions for our speaker, please send a direct message to Apurvaa in Excel events or an email to the address in the chat. We look forward to seeing you in the following sessions and expo booths. Thanks, everyone.